Hello students, today we're going to cover section 7.2, Similar Polygons. Our learning goal for today is to be able to identify and apply similar polygons. So the first thing we have is some vocabulary. Similar figures, much like congruent figures, have the same shape, but unlike congruent figures, similar figures do not necessarily have to have the same size. We can abbreviate is similar to with the tilde symbol. We define similar polygons to be two polygons that have corresponding angles that are congruent, and the corresponding sides must be proportional. So here we have two similar polygons, quadrilateral ABCD and quadrilateral GHIJ. We can see that positionally the angles are congruent, so angle A is congruent to angle G, angle B is congruent to angle H, angle C is congruent to angle I, and angle D is congruent to angle J. In addition to that, their sides are in proportion. So positionally, AB over GH is equal to the distance from B to C over H to I, and so on and so forth in the extended proportion you see at the bottom right-hand corner of the screen. We write similarity statements with the corresponding vertices in order, just like we did congruent statements. And when three or more ratios are equal, we write an extended proportion, which we saw in the previous slide. A scale factor is the ratio of corresponding linear measurements of two similar figures. So in this case, we have triangle ABC, which is similar to triangle XYZ. And if we're asked to determine the scale factor of triangle ABC to triangle XYZ, so here we can write the extended proportion. 15 is to 6, as BC or 20 is to 8, which is also the same thing as AC, which is 25, to XZ, which is 10. Reducing any of these will give us the scale factor, so I'll reduce this one by a factor of 5. And I'll reduce this one by a factor of 5, and we can see that the scale factor of triangle ABC to triangle XYZ is 5 to 2. So in order to understand similarity, we need to be able to understand which pairs of angles are congruent, and to be able to write the extended proportion for the ratios of the lengths of the corresponding sides. As far as the pairs of congruent angles are concerned, this is positional. So angle D, which is first position, is congruent to angle H. Angle E is congruent to angle J. Angle F is congruent to angle K. And finally, angle G is congruent to angle L. For the extended proportion for the ratios of the lengths of the corresponding sides, I like to do things in a very similar fashion. I'll take the first two letters of the first figure, so in this case DE, and I'll put it in ratio to the first two letters of the second figure, HJ. And I'll go straight down the line, so EF over JK equals FG over KL, and then the final statement is first to last, or DG to HL. The second type of problem, determining similarity, asks us, are the polygons similar? If they are, write a similarity statement and give the scale factor. Here we're given two measurements, 15 and 10, and we're given two measurements in the other figure, 20 and 15. If these two figures are to be similar, the long sides must match, and so must the short sides. So in this case we have to check, does 15 going to 20 equal 10 going to 15? So if we reduce the left-hand side, we get 3 over 4. And if we reduce the right-hand side, we get 2 over 3. Since 3 over 4 does not equal 2 over 3, the answer to this question is no. These figures are not similar. Since they're not similar, we cannot write a similarity statement. Same question, different figure. In this case, we're given two measurements. The 12 is repeated twice and the 18 is repeated 3 times. Over here, same thing, we have a 6 and a 9. The 6 is repeated twice, and the 9 is repeated 3 times. So in this case, the short number in this side, 6, must be to 12, as 9 is to 18. Reducing both sides, we can see this is 1/2, and this is 1/2. Since both numbers are the same, the short number appears twice in both figures, and the long number appears 3 times in both figures. These polygons are in fact similar. So in this case, we have to write a similarity statement. We can start with any letter we want, so here I'll start with A, and I need a direction, so I'll go around this figure A, B, C, D, E. So I have to pick one of the letters in this figure, which is the same as A. In this case, I'll choose S. We could have also chosen U. If I go from A to B, I need to travel towards the 90-degree angle, so here I have to go this direction around the figure. So I have SR, VU, T. So this is one possible similarity statement. If I'm going from ABCDE to SRVUT, the figure is getting smaller. So I want to write this going larger to smaller. So every 2 units on this figure represent a single unit on the second figure. Problem number 3 asks us to use similar polygons to find the value of the variable. Since the variable lengths here are lengths of sides of the figure, we will establish the extended proportion for the sides. So here we have AB over EF equals BC over FG, which equals CD over GD, which also equals AD over ED. Now let's fill in the information that we know. Here you can see I've taken information from the diagram and plugged it into the extended proportion. In this case, using the transitive property and these 2 values, I'll set up a single proportion, 5 over y equals 9 over 6. Using the cross products property, we get 5 times 6 equals 9 times y. 5 times 6 is the same thing as 5 times 2 times 3. 9 is 3 times 3 times y. 1 3 in this case cancels. Dividing both sides by 3, we get that y equals 10 over 3. So let's set up a proportion with these 2 now. We have 7.5 over x equals 9 over 6. Since I'm not a huge fan of dealing with decimals, I'll multiply both the top and bottom of this left-hand portion of the proportion by 2. So 7.5 times 2 is 15. And in the bottom we get 2 times x. And this will still equal 9 over 6. Using the cross products property, we get 2 times x times 9 equals 6 times 15. So let's do prime factorization of both sides. We get 2 times 3 times 3 times x equals 2 times 3, which is 6, times 3 times 5, which is 15. Here we can see the 2's and the 2 3's cancel each other out, and we get x equals 5. So we found the value of the variables x and y. X equals 5, and y equals 10/3. Problem number 4, also using the similarity, says that your class is making a rectangular poster for a rally. The poster's design is 6 inches high by 10 inches wide, and the space available for the poster is 3 feet high by 4 feet wide. And it asks, what are the dimensions of the largest poster that will fill the space? So here we have a mock-up of the situation. We have one poster that is 6 inches tall by 10 inches wide, and another space that is 3 feet tall by 4 feet wide. So first, let's get everything into the same units. So let's convert to the smaller of the two units. Let's convert these feet to inches. So 3 times 12 is 36, so we have 36 inches in this case. And 4 times 12 is 48 inches. So the space that we're looking to fill is 36 inches by 48 inches. So if we take this and try to fit it into a 36-inch space, we can at most multiply this by 6. 6 times 6 would give us the 36 inches. If we take the 10 inches and try to fit it into a 48-inch space, we can multiply it by at most 4.8. So we see here we have two possibilities. We could multiply by either 6 or by 4.8. If we were to multiply the 10 by 6, we would have 60 inches, which would be too large for the space. So we have to eliminate the larger of the two in this case and multiply both by 4.8. 10 times 4.8 we already know is 48 inches. So in this case we get the full width of the space. However, multiplying 6 by 4.8 we get 28.8 inches, which while it doesn't fill the space, does maximize the size of the poster. So the dimensions of the largest poster that will fill the space is 48 inches by 28.8 inches. So here we have our final vocabulary slide. In a scale drawing, all lengths are proportional to their corresponding lengths. The scale is the ratio that compares each length in the scale drawing to the actual length. The lengths used in a scale can be different. For example, a scale might be written as 1 centimeter equals 50 kilometers, or 1 inch equals 100 miles, or 1 inch might equal 10 feet. Scales are typically used in both maps and modeling. So our final problem of the day. The diagram shows a scale drawing of the Golden Gate Bridge in San Francisco, and the distance between the two towers is called the main span. It asks, what is the actual length of the main span of the bridge if the main span in the scale drawing is 6.4 centimeters? So here we have our picture, and in this case, this is 6.4 centimeters, the distance from this tower to this tower. So we're looking to find the actual distance of the Golden Gate Bridge between the two towers. We know that every centimeter on this drawing equals 200 meters in the actual bridge. So we take the 6.4 and multiply it by 200. So we have 6.4 centimeters, which we know, and we're going to multiply by the scale. So in this case, 200 meters is the same thing as 1 centimeter. So this gets put over a 1. The centimeters cancel each other out. So in this case, we know that our result is going to be meters. If we multiply 6.4 times 200, we get 1,280 meters. And if you want, you can convert that into 1.28 kilometers. Either of these answers would be accepted. So that concludes the lesson on section 7.2, similar polygons. Thanks for paying attention, and I'll see you soon.